My collaborators here at ANU, a lot of the experimental work, as I said earlier, I'm an experimentalist, so a lot of the experimental work is done at the Australian National University, and of course I collaborate with people here. Chris Klein, I'll mention his work at the very end. That's very exciting at the moment. So, okay, brief outline. The important part is defects for any kind of deformation or seismic properties, as I'll try to show. And we have to talk about some of the fundamentals. How do we think about defects? What kind of defects do we have, and what do they do? And that leads directly to flow laws. So, trying to reference. In the Earth, we have a very complicated system. So one of the problems is that a lot of these very fundamental relationships, the constitutive equations, were derived from very simple systems, that is metals, right? The first materials that man deformed more or less were metals, because you can deform, some of the metals, brass or whatever, at comparatively low temperature and make them flow. So a lot of the thinking comes from that, but of course we have silicates. So things are a little bit more complicated, and I'll try to highlight that tension between adapting things from the material science literature for very perfect, pure systems to our somewhat more complicated system where we have the entire periodic table at our disposal. And then water is one such defect. I'll talk a little bit about water, and actually that might change our thinking about defects in general. And then seismic properties at the end. So just as a reminder, rocks are beautiful, and rocks are also a little bit complicated. You can see that here. That's a natural sample, and I'm sure you'll see more of that. That is deformed. You can see there's elongation going on. What I'll be essentially, our thinking is that the properties of the upper mantle is dominated by the mineral olivine, right? So I'll be talking pretty much exclusively about olivine, but just as a reminder, it's again more complicated than that. You have other things like pyroxenes in there as well. But olivine here, this light green mineral, that's what I'll be concentrating on. So a little bit overlap, I think, with Phil. He talked about springs and dashpots, I think. So deformation, going back now centuries here, Hooke's law, right? You apply a force, then you have a material property here, the spring constant, and if you apply a force in the form of these weights, then you get an elongation of the spring, right? And essentially what I'll be concentrating on is the spring constant. So there's a linear relationship here between the applied force and then the elongation, and the translation here is done by the spring constant. For the Earth, or in general for all solids, I should say, it's a little bit different. The restoring force, instead of little springs everywhere, of course, you have atoms in an equilibrium position in a crystal lattice. So regular crystal lattice, and you can see this is a very simple lattice. Regular crystal lattice, and so the equilibrium position of these individual atoms is determined by the potentials, the electrostatic interaction. You have a positive nucleus, negative electron shell, so you're trying to optimize the arrangement of these atoms, and you end up with this potential here, a sum of repulsive and attractive energies. Right? And you can see that this potential, there's a position where the energy is at a minimum. That's at 0 Kelvin, that's where the atom will be. Of course, as you increase the temperature, you probably know that well, the atoms begin to vibrate, essentially vibrate in this energy minimum. And you can see that the energy minimum is not symmetric, so the vibration is not harmonic, like you take the spring and you elongate it and vibrate. As long as you keep tapping it with the same force, it'll vibrate harmonically. Here the atoms vibrate anharmonically, and you might hear me use that term, anharmonic temperature dependence, right? The higher the temperature, the larger the deviation from the equilibrium position. So you can translate that into a force similar to the Hooke's law, where instead of a force, here you have stress, sigma. The spring constant is an elastic modulus. That's what you measure macroscopically here. You measure an elastic modulus. E is the Young's modulus. I've listed the moduli here, bulk modulus. I'll be talking later about the shear modulus. And then instead of an elongation x, you have a strain epsilon, right? So that's the introduction of the terminology stress and strain, and the relationship, what translates one into the other is this elastic constant. So moving on to deformation, stress is modulus times strain, right? Here's Hooke's law. For ice, you can measure this G, this shear modulus, and it's about 4 gigapascal, so, or 4 times 10 to the 9 Pascal, and let's say strain is 1. It's very clear that the ice flows, right? This picture illustrates very nicely ice is a polycrystalline rock, basically. It consists of crystalline grains, but somehow, even though it's a solid, obviously, since it has crystalline grains, it flows. You see that very nicely. So we relate directly the stress to the modulus, but what is the driving force for the system? The driving force is gravity, right? The ice flows down the hill from the glacier here into some valley, linking directly to Alaska. So if you look at the driving force, the stress, and you can write that down very simply, is density, so is rho gh, density, acceleration due to gravity. Again, gravity is our force here, times the thickness of the ice sheet or the glacier. And if you just make very round numbers here, this is just order of magnitude estimate, the density, 1,000 kilograms per cubic meter, acceleration due to gravity, just take 10 meters per second squared, and say the glacier is 1,000 meters thick, you get something that is 10 to the 7 Pascal. Right? So 10 to the 7 Pascal. But then here we said from Hooke's law, the modulus is of the order of 10 to the 9 Pascal. So there is a contradiction, and that contradiction was realized, as I said, when people started deforming metals, that the ideal elastic constants are such that you should never be able to deform anything, right? You should never be able, this is like 2 orders of magnitude. It's actually quite a bit worse, right? If you think about mantle convection, the elastic moduli are of the order of 100 gigapascal or so for silicates, and that's pressure dependent, and the deeper you go, the higher the modulus. But it's of that order. The convective stresses are of the order of 1 to 0.1 megapascal, right? So you have many orders of magnitude differences between what Hooke's law says, the force that you need to cause any kind of deformation, and the forces that you actually have that do deformation. And the difference is, of course, that this perfect elastic world, this perfect world of a crystallographer or a physicist, has to be modified, and it's not quite as perfect. And those are the defects that I'll spend the rest of this lecture talking about, right? So defects make deformation possible in the first place. Otherwise, there would be no deformation. Everything would be frozen and static. So defects then, why do we have defects? That's another key question, and I have to do a little bit of thermodynamics, just very briefly go into that. So we have the internal energy, right? And that's what I showed earlier, this potential here, the internal energy here with the equilibrium distance, the equilibrium spacing between atoms, this potential. In the Earth, it's very important we not just have an internal energy, we also have pressure to work with. That's another important distinguishing aspect to material sciences in general, that material sciences, they don't have to worry that much about pressure, whereas we really do in the Earth, even in the upper mantle. Pressure is a very important, has important effects on this. And therefore, we talk about an enthalpy rather than just an internal energy. So just as a reminder, that is in the back of all of what I'll be talking about, that we always have to think about pressure as well. So fundamental state functions, enthalpy, but the more interesting one, of course, is this one here, entropy, right? And entropy is a measure of the state of disorder in the system. And the simplest example, and what I'll be coming back to, is configurational entropy. You have 2 compounds, A and B, and nice separate compounds. If you take different colored marbles or something like that, you can either keep them completely separate, then you have a very low entropy, or you can mix them perfectly, then you have a very high entropy here, right? So compound A and B, and at a 50-50 mixture, your entropy is maximized. You have the maximum disorder in the system. And to visualize that, right, so this is the parents' bedroom, very boring, very ordered. You can find everything all at once, but that's usually not how it works. And then there's the kids' bedroom. Right? You increase the entropy by just entering because you step on things and break things and they get even more disordered, right? So visualizing entropy here. What does that have to do now with the reason for defects, right? So thermodynamically, why do we have defects, right? We have those two state functions, enthalpy and entropy. And if we think about taking that perfect crystal lattice and we take an atom out, we rip one out of an equilibrium position, that certainly requires energy, right? The atom is happy in its position, but if we take it out, we distort the crystal lattice surrounding it, and we have imperfectly satisfied bonds surrounding it, right? So there's certainly an energy or enthalpy penalty for taking an atom out and removing it from the crystal, right? So the enthalpy increases as we create a defect. But if we create a point defect, we also increase the disorder in the system, right? So as we take an atom out and the crystal is perfect before that, it becomes a little less orderly, right? And that means the entropy increases. So the total state of the crystal is characterized by the Gibbs free energy, which is the sum of this enthalpy here and the entropy. So the Gibbs free energy is the sum of these two, and so we have to look at what happens if you plot here energy, Gibbs free energy. Here's the enthalpy, so the more atoms, and here's defect concentration. The more atoms we take out, the higher the penalty we pay, the more energy we have to be prepared to spend to take these atoms out. On the other hand, as we do that, certainly initially, we get something back in the form of entropy, right? We gain entropy. The entropy increases as we introduce more and more defects. So those two are in competition with each other. The only difference is that as the enthalpy is just a linear increase, the more defects we have, the higher the enthalpy penalty that we have to pay, but the entropy gain levels off at some point. Right? There's no further, basically, the disorder is already such that, yeah, nothing else happens. So, this levels off. So the net is that for a high defect concentration, the Gibbs free energy increases. But in between, there's a minimum here, right? So there's a minimum where your gain in entropy outweighs the penalty in the enthalpy. And that's the equilibrium defect concentration here, the minimum in the Gibbs free energy. So even a perfect crystal will always have a finite number of point defects because of this entropy term contributing to the total Gibbs free energy. So yeah, for small defect concentration, of course, you have a greater entropy gain than an enthalpy penalty, so a finite concentration of point defects. And that sounds very abstract, but going back to the way I motivated that, you can't deform things without defects, right? So, this is a theoretical concept to some degree, but on the other hand, you can see that very easily because you need something other than the perfect elastic moduli to deform materials. So, zooming in a little bit, what kind of defects do we have? And again, starting out with a perfectly simple lattice, sodium chloride, the different color-coded ionic species here. And we're talking first about point defects, right? This is what I was talking about in thermodynamically as well. These are point defects. And moreover, I'll distinguish between intrinsic defects, meaning defects that only relate to sodium and chlorine. In this initially perfect crystal, you have two types of defects. One you can have, and the key part here is if you look at defects, they always have to be charge balanced, right? So the sodium and the chlorine have opposite charges. If you take one out, a chlorine ion, you have to also take a sodium ion out in order to charge balance this. That's one of the rules. Macroscopically, you always have to have charge balance. So practically, that means when you write down defect equations, that's the first thing you have to look for, that you actually charge balance all your defects, right? You can't just take one out, but leave the other in there. So that was realized early on, and then people came up, Schottky and Frankel came up with different defect models, and you might recognize, right, this is the early transistor semiconductor view of the world, right? This is where a lot of this was developed for semiconductors. So you can have interstitial atoms here, right? So you take a sodium out of its lattice position and put it interstitially. Electrically, that's still neutral, right? Macroscopically, you have the same number of sodium atoms as before. You just take one out of its lattice position and put it interstitially. Or if you have vacancies, so one of them is missing, you can, in terms of vacancies, you can take a sodium out and you can take a chlorine out and a sodium out, right? So that's the other way of keeping the crystal charge balanced. And it's really interesting already here, you can start wondering what the effect of pressure is, for example. Those are things that I don't know that we actually understand that perfectly, right? You can see that if you want to create interstitials, there may be a penalty due to pressure, right? Which you don't really have at 1 atmosphere, but at higher pressures, interstitials might not be very favorable because obviously, again, you distort the lattice, you have to blow it up a bit. So energetically, it might be unfavorable to have interstitial defects rather than vacancies. On the other hand, that might not be that clear cut because the crystal structures for the silicates that we're looking at are much more complicated than that. So I'll come back to this a little bit. Then the other type of defect, instead of having only intrinsic defects, only the original sodium chloride, you can also have extrinsic defects. And again, a semiconductor, gallium arsenide, you can dope this with all sorts of other ions here, indium, boron, and you get different properties. So here, defect pairs, you get different properties depending how you dope it, right? This is basically, again, how you develop semiconductors and other materials where you fine-tune the properties. In the Earth, of course, as I said, we have the entire periodic table present, so you can't fine-tune. You have to take the opposite approach, right? You have to figure out what is actually in there, in the olivine, for example. What are the dominant defects, the intrinsic versus extrinsic defects? What are their concentrations? And how does that affect the properties of the crystal? So point defects, and I'll come back to them certainly some more, but I just want to make sure if you step up macroscopically, you have line defects, and I think Phil already talked about dislocations. This is an image showing screw dislocations in olivine, so I won't talk about that further. I think Jessica might also relate to dislocations, what they do during deformation. But just to be aware, the one difference between point defects and these more macroscopic defects is that here you can't treat them anymore thermodynamically, statistically, like with Boltzmann statistics, right? These are macroscopic objects. And then grain boundaries, very important, and I'll spend a little bit of time on grain boundaries. Grain boundaries, again, going back to the pictures that I showed early on of rocks, grain boundaries are present in all rocks, right? You have both interface boundaries between like phases, and then obviously as you have olivine and pyroxene, you also have boundaries between those grains. Right? So grain boundaries are always present in all rocks and are very important type of defects. And that's again, grain boundaries in silicates are by far not as well studied as grain boundaries, for example, in semiconductors or in metals, right? So that's again something that's fairly open, and advances in electron microscopy certainly make it possible to look into grain boundaries and their properties in much more detail. The reason why grain boundaries are so important is that they affect diffusion, and I'll come back to diffusion. Deformation then is built on diffusion frequently, seismic properties, electrical conductivity, pretty much everything at some point, any macroscopic measurement of the rock interacts with the grain boundary. And therefore, we need to understand it. It's a lattice defect, so the very simplest view is that you just stack up a whole bunch of dislocations, right? And the dislocations give you a distortion in the lattice. You can see the lattice planes here are at an angle, this angle theta here, and you can geometrically describe if you have, depending on the dislocation spacing here, you get a relative orientation of the neighboring lattice planes. And that lattice misorientation by this angle theta, then you can take and define your grain boundary. And grain boundaries are typically defined as having misorientations between 10 to 15 degrees. And I'll show that, I think, in the next slide a little bit. So essentially what you're looking at is the energy, the energy of the grain boundary relative to a perfect crystal. And melt, as it turns out, if you add melt to a system, it's a very sensitive indicator of grain boundary energy. So what you see here, that's again a transmission electron microscope image, a TEM image at somewhat lower resolution. You can see here dislocations. These are individual dislocations that are arrayed to form a subgrain boundary. Here you have a high angle grain boundary, so something that has a misorientation greater than 15 degrees, except that you can't see the lattice planes. I'll show some images later on where you can see the lattice planes of the neighboring grains, but here you can't see the lattice planes. You can just measure the orientations of the neighboring crystals and say that this is a high angle grain boundary, meaning greater than 15 degrees. And the melt here, the melt in glass, you can see that it doesn't penetrate very deeply into the subgrain boundary. And if you think about that, so you can write down an equation. This angle theta here refers to the angle between solid and melt, right? So unfortunately it's the same theta, but it's not the misorientation of the previous slide. This angle theta here is very large, meaning that it's unfavorable for the melt to penetrate on the grain boundary into the subgrain boundary, right? That's a very large angle. So this subgrain boundary expels the melt. It cannot lower its energy state by drawing melt into it. On the other hand, a high angle grain boundary has a very small dihedral angle, so melt is drawn deep into the grain boundary, meaning that energetically this grain boundary here, this high angle grain boundary, has a much higher energy in comparison to the subgrain boundary. And that goes back to the definition, of why we say grain boundaries are defined by this misorientation angle of 10 to 15 degrees. The subgrain boundary has a misorientation of a few degrees. It has a low energy. It wants to, for example, expel melt. Energetically, it looks different than a high angle grain boundary. And by the time you get to something like 10 to 15 degrees, it doesn't really matter. But if you further increase the misorientation, the grain boundary energy doesn't change very much, right? So that's why people typically, and you can show that with the experiments, I won't go into the details there, but essentially that's a typical a misorientation, relative misorientation of 10 to 15 degrees. So yeah, visualization of type of grain boundaries. Now the high resolution images, we zoom in basically and we can start to see lattice planes. So these are 010 lattice planes in olivine. At very high resolution. Here is a grain boundary. This grain here, that's a high angle grain boundary. This grain here, you can't see the lattice planes. That is one of the things I'll show next. A couple of higher resolution images where you can actually start to see lattice planes on both sides of the grain boundary, right? So this is, you can see here, this is 1 nanometer. The lattice spacing is of that order, essentially. So you have to be able to resolve nanometers or better in order to create these lattice fringe images. And the idea here is that this is ab initio modeling, so progress on that side as well. A lot of people now are doing ab initio modeling, although grain boundaries are still pushing it because you can't essentially model yet a large enough ensemble of atoms that you can get away from edge effects of your model domain and actually model grain boundaries. But this is one of these attempts. What you can immediately see is that, similar to this image here, you have a region that is not as ordered as the perfect crystalline lattice, right? This is very ordered, the grain interior. The grain boundary is more disordered, right? So you can see that in the TEM images, and this is work, that Katharina Marquardt is doing, looking at, so as I said, I mean, comparatively little work has been done on grain boundaries in olivine, even though they're very important. These are now higher resolution images that you can produce with more modern electron microscopes. And you can start to see structure on, here's the grain boundary, on either side of the grain boundary, right? So you have two different types of grain boundaries. And then, of course, if you start to get images from different grain boundaries, you start to realize grain boundaries are different. And that's certainly work in progress. Here, the scale bar, 2.5 nanometer, again, very high resolution. The problem is, of course, with the TEM that, yeah, 2.5 nanometer, so the grain size of a rock, a natural rock, is of the order of millimeters to centimeter, right? So you can imagine how many grain boundaries are you going to be able to look at with the TEM. And that's an intrinsic problem that we really need to look at. You know, you have, you know, for random orientation of crystals, you have an infinite number, so to speak, of grain boundaries, because it's the two grains, the crystal and lattice, and the grain boundary plane in between them. But you can only look at a very small number, right? So any of these, there's a premium on looking at these, and these are actually experimental samples. So understanding of grain boundaries, but you can see again that, you know, certainly there's a region here where you neither have the symmetries and the properties of the grain interior of this grain or this grain. It's more disordered. And more disordered then means, for example, diffusivities will be higher along the grain boundary. There are models that invoke grain boundary sliding. I'll touch on those. So all of these models, in the end, fall back on what we know about the properties of these grain boundaries.
Question?
Yep.
Just a simple one.
Yep.
These two diagrams shows very different look of the grain boundary. One is quite sharp, and the other one is very diffused.
Yep.
Are these a result of the instrument, or is it true?
Yeah, this is an ongoing debate, right? This is an ongoing debate. It's not entirely. It's not very easy to get these images. Essentially, you have two crystal lattices, and you know, you have a TM foil that's thinned enough so the electrons can go through the thinned material. And then if you tilt the grain boundary, you can get an apparent overlap of the lattices on either side, because your transmitted electron beam goes through both lattices, and it looks like they overlap. So one of the key things in this, I mean, this is very painstaking work, is that you have to align the grain boundary parallel to the electron beam, and then you can actually distinguish, then you can get, and then, okay, so you have the grain boundary aligned to the electron beam, then you have to align both grains, so you have to tilt in 3 dimensions, right, in order to get these lattice planes to show up, because if you're inclined to the lattice planes, you wouldn't see them either, right? But then it turns out, if you go through all this trouble, try to align your grain boundary and then tilt, you know, more to try to get lattice planes visible, then you do get different images, different grain boundaries. So the orientations, the relative orientation, without, yeah, didn't want to go in that many details, but basically, right, you have the orientation in 3-dimensional space of the crystal lattices, and then you have the relative grain boundary plane orientation. So you have 5 parameters essentially that describes your grain boundary plane. How to rotate one crystal onto the other, and then the orientation of the grain boundary plane. So all of that you have to take into account, and then it turns out, I guess not that surprisingly, that you have different grain boundary geometries. You have different grain boundaries. Some of them, it's easier to match the crystal lattice from one side of the boundary to the other side, and some of them that are more disordered. And we see that, for example, when we look at melt distribution, we have some grain boundaries that are wetted by melt, other grain boundaries are not wetted by melt. So again, there are energetic differences between different types of grain boundaries. But the problem, again, is that you have to do statistics on that. How common, you know, this is just accidental, right? You thinned your plane, you thinned your sample such that you can shine the electron beam through, and it's just completely accidental where you end up, what grain boundary you see in a fine-grain experimental sample. So then you have to step back and do statistics. You know, how common is this versus how common is that? So it's non-trivial, and that's ongoing work in Bayreuth, for example. One aspect that's agreed on is that grain boundaries chemically enriched in trace elements. So olivine, again, going back to the idea, you have your entire periodic table if you can analyze it. But it turns out that grain boundaries, consistent with the idea that grain boundaries are somewhat more disordered than the grain interior. So olivine contains calcium, titanium, aluminum, nickel, chromium, sodium, lithium. You can go down the periodic table. All these are trace elements that are in, if you analyze that with the electron probe or with laser or mass spectrometers, you can analyze olivine grain interiors that can contain all of these things. So what I talked about earlier, this links back to defects. These are creating defects because they don't, some of them, certainly sodium is 1+, magnesium is 2+, the ions. So that creates a defect because you have to then charge balance it, right? It doesn't slot in perfectly in the crystal lattice. So all of these are present in the grain interiors, but then if you analyze grain boundaries, and again, that's something that's becoming, that improves analytically, that you can actually, so this distance here is given in nanometers, that's +5 nanometers. You can see that the grain boundaries here, in particular calcium, for example, titanium, these are enriched in the grain boundaries relative to the grain interiors. So there's the notion that sometimes that's called segregation. Segregation, in my mind, is a little bit, because it's really an equilibrium partitioning, right? It's a partitioning between the grain interior and the grain boundary, and if you have other phases present, such as other pyroxenes or melt, it's an equilibrium partitioning between all the phases in a system where the grain boundary acts as a phase in terms of the chemical element partitioning, right? Grain boundaries are enriched in these elements. So, okay, now we've talked a lot about defects, so point defects, line defects, grain boundaries. Now we're trying to put that together and come up with flow laws. And there are, again, going back to the material sciences, first principles, derivations of flow laws, so physical model, and then I'll introduce one for diffusion creep very briefly. These are the constitutive equations relating then, stepping back to the deforming glacier or to the convection in the mantle, relating your stress, your driving force, to the resulting strain rate, right? That's what you're trying to link with these constitutive equations. And one book that's quite old but describes it very well really is this one here by Poirier, Creep of Crystals. It describes very well the original models that are behind this. So very briefly, that relates directly to the experiment you did last week with the dead weight apparatus. Essentially, in the air, in any kind of fluid, you have a hydrostatic stress, state of stress, but with the dead weight apparatus, you created a non-hydrostatic state of stress, and because of that non-hydrostatic state of stress, you started to deform the material, the wax that you looked at. If you look at this macroscopically and try to come up with a model, basically a non-hydrostatic state of stress will affect your defect concentrations. Right? That's really the key part here, that non-hydrostatic stresses will affect defect concentrations. And you can sort of imagine that if you have a higher stress in the horizontal direction in comparison to the vertical direction, and all stresses in the Earth are always compressive. Here it's drawn as a tension, but it works with different compressive stresses. So you have your sigma 1 and your sigma 3. Sigma 1 would be the dead weight. Sigma 3 would be the confining pressure of the surrounding air in your dead weight experiment. So that stress difference between one side here under compression and then one side under tension affects the concentration of defects, right? Because we said defects have something to do with energetics, energetically favorable, what is the energy penalty? So the energy penalty, as you introduce this non-hydrostatic stress, changes such that here under compression, you have a lower number of vacancies, for example. You decrease the number of vacancies on the side under compression, and you increase the number of vacancies on the side under tension. And then, of course, as I said, you can't just flow vacancies. You also then have to have a counterflux of atoms. So if you put all of this together and you keep, in your dead weight experiment, keep creeping it, then eventually you change the shape of this material, right? You start from a square or a right cylinder, and as you flow long enough, through the diffusion of vacancies, counterflux of atoms, you eventually, vacancies in atoms, you change the shape of this material, right? So that's very briefly, and then basically, but really the idea is that your non-hydrostatic stress changes defect concentration, and you can calculate that there's a path length, of course, here for the diffusion, which is the grain size. So if this is one single grain, right, D is the grain size, you have to diffuse of the order of the grain size in order to make that change in shape. So if you then put that together, so you have a differential stress, that leads to concentration gradients of your defects, that leads to diffusion, right? Same as chemical diffusion. If you have high concentration, you try to get to a uniform concentration by diffusion. That's the same principle here. Concentration gradient from phase A to B, there's a length scale involved, that's the grain size. And diffusion, that's then diffusivity of the atomic species. And it also depends on the crystal structure, right? Because you have to, in this particular example, you diffuse through the crystal structure. And this is where temperature comes in. Right? Temperature is a key player in all of this because diffusion is temperature dependent. So here at the bottom is your constitutive, your pure constitutive equation, right? If you work it all out, here's the grain size, right? Your length scale. And then here, this dsd, that's the self-diffusivity of these different atomic species that are diffusing through the crystal. And that self-diffusivity is dependent on temperature, right? And so that's an Arrhenius behavior here. That's where your temperature dependence comes in. So, and not only temperature dependence, right? So again, the idea that we have an enthalpy, you also have a pressure dependence, which becomes very important in the Earth. So temperature dependence, pressure dependence, this is your basically pure constitutive equation. Here's the atomic volume in there. What you do experimentally when you do a dead weight experiment, right, you don't measure directly the atomic volume and so on. You basically measure what you did. Presumably you have an applied stress, that's the weight that you put on the sample, and you can measure a strain rate, how fast is it flowing, right? And then you know the temperature, right? So room temperature. So those are the things that you can measure or control in your experiment. And then really you lump all these parameters that you can't directly measure into a constant. Right? You can measure the grain size, that's another part that you can measure. Of course, you can measure the grain size, but then you have this experimentally, if you see flow laws, they will be of that form. So the strain rate, how fast the material is flowing, dependent on the stress. And for diffusion creep, that's linear, a linear dependence, one-to-one correspondence of stress and strain rate. And then grain size here, the grain size has an exponent, right? So that if you do the derivation, if you do the geometry here, you get a squared. So this grain size dependence enters squared, right? And that's what you have in this constitutive equation here. You have a squared grain size dependence. And then everything else, you know, all these other constants that are in there are really lumped into one. And that's what you just fit that, you fit the data, you measure stress and strain rate, you fit your data, and you get an exponent, or you get a pre-exponential constant A that contains everything else. Sometimes when people you know, work with these equations in flow modeling, for example, that A is sort of a little bit neglected, or parameters such as the activation energy, right? So E is the activation energy in this particular case, how temperature sensitive the process is. This A is neglected when other parameters are varied. But really experimentally, we fit all of this as one, you know, to one set of data. So if you start to change E, then you really have to also start to change A, right? So A is really dependent or is part of the fitting process of your experimental data, even though it's just this constant. Right, so that's a constitutive equation for diffusion creep, where diffusion happens through the grain interior. And right, if you actually do deformation experiments, so I'm not going to show any data, it turns out what you measure is not a squared grain size dependence, but rather a cubic grain size dependence. And that gets then back to the grain boundaries, because a cubic, you can also derive one of these, constitutive equations for the case where you have diffusion along grain boundaries instead of through the grain interior. So, diffusively, if here you're diffusing through the lattice, it turns out that as grain size increases, it becomes energetically favorable, or it's faster, basically, to diffuse along the grain boundaries. And that's the reason why I started talking about grain boundaries. Grain boundaries are more disordered, so it's easier, it's faster, it's a fast diffusion pathway. So typically, when we do deformation experiment, we find cubic dependence of the grain size, indicating that we have grain boundary diffusion rather than grain interior diffusion. But otherwise, it's the same form of the equation. And now we have to add one other complexity in that, I'll show that a little later. So again, for a silicate like olivine, right, you have magnesium, iron, silicon, and oxygen. So this is the problem, one problem here. If you then look at atomic volumes or molecular volumes, which one is the right volume to use? And it turns out, if you do the experiments, there are different diffusivities for these different species. So diffusion is rate controlling. What's plotted here is the diffusivity as a function of temperature, or rather inverse temperature, for, in this case, olivine. So silicon, oxygen, and then magnesium. These are grain interior diffusivities, so diffusion through the crystal lattice. And then these are grain boundary diffusivities. You can see, again, silicon, magnesium, and oxygen, and their order is different. But if you look at silicon, so these are the grain boundary diffusivities, these are the grain interior diffusivities. If you look at silicon, in both cases, silicon is the slowest diffusing species. And I'll refer to that again as well. Silicon is surrounded tetrahedrally by oxygen, so with a very tight bond. So silicon, just from the bonding arrangement, from the way it's located in the crystal structure, is more difficult to diffuse. It's the slowest diffusing species. So for the total strain rate, because, so this is where it gets interesting, right? Because you're linking a macroscopic observation, a strain rate, with a microstructural model, right? And then you say that overall the strain rate is controlled by the slowest diffusing species diffusing along its fastest path, right? The slowest diffusing species in this case is silicon. Diffusing along grain boundaries is the fastest path, and that's then the rate limiting step, that's the rate controlling step for diffusion. So these are obviously lots of experiments, so I'm just touching on a very wide literature here, diffusion literature, lots of experiments, not as many as we want. And it turns out it's very interesting that oxygen grain boundary diffusion is actually the fastest of the diffusivities, whereas for grain interior, oxygen is slower than magnesium. Right? But for the model of deformation, what limits the strain rate, how fast you can deform olivine at a given temperature, is the diffusion of silicon along grain boundaries. Keeping in mind that this is a model, right? We don't directly observe the silicon diffusing through the olivine. We just have diffusivity measurements, we have deformation experiments, we measure as much as we can, and then we make a correlation between, with the background of these constitutive models that we have, we link all of that together and say, that's what's happening. Keeping in mind that's a model. So, one other wrinkle in this, and grain boundaries come back into this, is that pure diffusion, and that's already, in the earlier diagram that I showed as well, if you had really pure diffusion, you would change the shape of these crystals, right? That's exactly what we had, a shape change. So as you compress more and more, the initial square becomes elongated into a rectangle. But if we look at the microstructures, that's an SEM image now. You can see sort of almost ideal hexagonal grains. Of course, they're not exactly hexagonal, but this has a fairly ideal foam structure. You can see that even after deformation, that's a common observation in materials, that the grains are not elongate to accommodate the strain, but the grains actually remain more or less equiaxed if they are deformed only in diffusion creep. Right? So grains remain equiaxed after deformation. That was observed early on in the material science literature as well. So that led to the concept of diffusionally accommodated grain boundary sliding, that actually diffusion just accommodates. So here, this is the model before deformation, you apply a stress, and then diffusion just accommodates the grains sliding past each other. But in the end, right, you have a macroscopic shape change, but the grains are still equiaxed. So it's even more complicated than that. Diffusion just accommodates that neighbor switching in the grains during deformation. And again, this is to some degree empirical. You just observe that the grains are more or less equiaxed and haven't undergone this shape change. So you have to come up with another model that explains that. So moving on a little bit here. So diffusion creep, a linear relationship between stress, so stress here, strain rate, and then at higher stresses, you transition into what's called dislocation creep. And now the relationship between stress and strain rate and stress is that the stress has an exponent that is larger than 1, so you have a power law creep. Right? And that's typically dislocation creep, and that's something that Phil touched on. I won't go into any more details. So now we have to talk about the influence of water. So going back to defects, what are the defects, again, that enable the deformation? Again, such creep law as we had earlier, stress, so this n can be 1 for diffusion creep, 3.5 for dislocation creep. Here is the grain size dependence, 3, so p is 3 for diffusion creep. This drops out, basically, p is 0 for, it's not grain size sensitive for dislocation creep. And that's really important because dislocations are grain internal. So the deformation process does not rely or does not scale with grain size. So the grain size drops out. And then we can add one more variable here. This is either the water fugacity or the concentration of water, and it has its own exponent. Right? It has this exponent r, so we have stress exponent, grain size exponent. Now we have an exponent of this concentration of water. And here is again, that's the energy, but in reality, you have to add a pressure term here as well, so that you have an enthalpy here. So influence of water, the viscosity, right, just as a reminder, is the ratio between stress and strain rate. This is for Newtonian, but it gets a little bit more complicated if you have nonlinear relationship between the two. And just as another reminder, an important aspect of dislocation creep is that the viscosity then becomes stress dependent, right, because of this nonlinearity here, so that if you calculate viscosities leaving everything else constant, here the stress is 0.1 megapascal, here you have 1 megapascal, right? The calculated viscosity, this is just for the upper mantle, the calculated viscosity varies as a function of stress. That's something important to keep in mind. That's not entirely maybe intuitive, that as you increase the stress, the viscosity actually decreases for power law creep. But going back to the influence of water, okay. Yep. So it has been known, and this goes back, so these are papers from 2003, but the experiments showing that water affects the rheology of olivine go back much earlier into the 80s, and before that, people started thinking or observing, in particular also for quartz, that water does weaken rocks considerably in deformation. And this is a compilation from 2003 from Hirth and Kolstad, in this case, concentration here of water versus strain rate. The same thing here, that's really some kind of strain rate overall versus concentration of water. And what was observed is that there is a near linear relationship between how much water is there and how much the strain rate decreases here. So, or strain rate, sorry, the strain rate increases with increasing concentration of water. Right? The more water you put into the mineral, the higher the strain rate, leaving everything else fixed. Right? So in the earth, the more water, the higher the strain rate. The question is, so I'm talking here very loosely about water, right? The question is, you have a crystalline material. Where is water? What does water mean for a nominally anhydrous mineral such as olivine, for which the crystal structure originally does not include water, right? So I do have to show that because I'll refer back to it. So olivine, and notice that this is phosphoride, pure phosphoride. You have on this side here, on this M side, the M sides, magnesium and iron for typical upper mantle olivine, 10% iron on these M sides. These are octahedrally coordinated, these M sides surrounded by these oxygens here in red. And then these are the tetrahedra, that's silicon here. Right? You can see the silicon is tightly surrounded by these oxygens. So diffusion then, or anything else that you do in a crystal lattice, has to take these lattice sites into account. And you can see that in 3D, that's starting to look a lot more complicated than your sodium chloride. And accordingly, you have to treat it in a more complete manner. So defects, again, this is where models and desire to measure something experimentally collide to some effect. So the dry model of defects. So what is the dominant defect in a dry olivine? Which defect is the most abundant, right? And these are experiments going back here to the 80s. Essentially what was done is you subject the olivine to different conditions. Iron-bearing olivine, you can vary the oxygen fugacity. And then as you change the oxygen fugacity, you basically weigh the crystal. And weighing, then you're counting the defects, right? So you change the conditions that the olivine is exposed to, you weigh it, and that is a way of measuring defects. Of course, you can imagine that's a very indirect way. You by no means know exactly what the defects are. You just weigh the crystal as you change temperature, oxygen fugacity, and so on. And then you come up with models which defects are possible. And we already saw earlier, right, there's a whole range of defects that are possible. Interstitials, vacancies, we have different atomic species that can be defects here. So there was a lot of work going into this, and in particular these guys and others following up on this. And the equation that's written down, right, I won't go into too many details, that's Kruger-Wink notation. Essentially you're trying to say, right, we have, in this case, missing atoms on lattice sites. So the most abundant defects in olivine are these M-side vacancies, right? So you have in this particular configuration, M-side vacancy means that there is a magnesium ion missing, right? So you take one of these magnesium ion out, and that's what's denoted by this V sub M here. You have a vacancy of a magnesium ion, and of course, right, the magnesium is 2+, so this double prime here indicates that you have 2 negative charges as you take the magnesium out and remove it from the crystal. We have to have charge balance, and the charge balance is done by iron, right? This is iron-bearing olivine. Iron can change oxidation state. This is where it becomes really interesting, because as a function of oxygen fugacity, what the oxygen partial pressure is, you can change the oxidation state of iron, and the iron, it's 2+ certainly, is very similar to magnesium, so it sits on that M side, but you can also put an iron 3+ on that M side, and you can see that you need twice as many of the iron 3+ as they are magnesium vacancies to have a charge balance, right? So you have 2- here, you have 1+ here, so you 2 times as much, and that's what that notation says, that this overall is the most abundant defect in the olivine, right? But that's a model, remember, because all it did was weigh this and change the oxygen fugacity, change the concentration of these 2 defects. So this is where, there's a tension currently. Water and olivine, going back to where, so this in dry olivine, ideal olivine, these are the defects that you have. If you go back to water and olivine, where does the water sit in the olivine crystal structure? And you can do that much more directly by looking at infrared spectra. So you can do what's called Fourier transform infrared spectroscopy. You shine infrared light through the crystal and observe the absorbance. And it turns out that in natural olivines here, and a whole range, there's many papers, there's a very large literature by now out there, that the dominant absorption lines here, this is wave numbers versus absorbance, the dominant wave numbers for absorbance are at these 2.3525 and 3.572 centimeters to the -1. That's where your infrared spectra say your hydrogen is structurally incorporated in the olivine structure. And the way to look at this, yeah, I can jump forward. So again, ab initio calculations and actual observations such as infrared spectroscopy start to converge. If you replace, so one of the, in this case, particular case, you have a silicon vacancy, and to charge balance that, you add a titanium, which is 4+, like silicon, but the titanium sits on a magnesium site. This is a magnesium site here. And the charge balancing is done by 2 hydrogens. And what you see in the infrared is basically the vibrational energies here of the hydrogen coupled to the oxygen. And the hydrogen, of course, is surrounded by the larger crystal structure. That gives rise to these particular absorption bands, right? So that tells you, if you have these localized absorption bands, that tells you that hydrogen is incorporated in the olivine crystal structure as a defect compound, right? And again, not entirely straightforward because you have to worry about charge balancing, right? Everything has to be charge balanced, just like for your intrinsic defects where you have magnesium vacancies charged balanced by iron 3+. Here you have hydrogens charged balanced by this defect complex involving a silicon vacancy and a titanium atom. Right? So going back, there's a lot of work done on trying to figure out, so I said earlier, right, you have all sorts of extrinsic defects, calcium, aluminium, chromium, nickel, and so on in the olivine lattice. And so now, how do these extrinsic defects relate to your infrared spectra? And yeah, I should get a better slide for this, but basically, people like Andrew Berry have doped olivine with all sorts of materials, iron, manganese, chromium, vanadium, titanium, scandium, for example, that have different valences, different charges of their ions, and then looked at the infrared spectra, right? Hydrated olivine and looked at the infrared spectra, and you can basically fingerprint each particular defect has a particular absorbance in this, in the infrared, for the infrared spectroscopy. Here, this tetrahedral, that's silicon, right? So this absorption band here is silicon. This here, as it turns out, is titanium. And that's, these 2 titanium peaks correspond exactly to those 2 titanium peaks that you see in the natural crystals. And then you have, for example, iron, but you can see that, here's titanium, here's silicon. Here, if you dope your olivine, if you oxidize the iron, you have more iron 3+, basically, that shows up here. And magnesium vacancies really are at this highest energy, lowest wave number here in this region. Magnesium vacancies are essentially insignificant, right? Across all infrared spectroscopy, it's very difficult to get significant absorbance in this magnesium vacancy region where, the canonical dry model says you should have lots of magnesium vacancies, right? This should be the dominant defect. But if you hydrate the olivine at least, you basically, this is insignificant. The number of hydrated magnesium vacancies you get are insignificant. So there is a tension with the dry defect model in that if this is really the dominant defect, for some reason, either it's not there or you don't hydrate it, right? You can't really say that. But for hydrous olivine, it's not an important defect. Whereas, by contrast, titanium is an important defect. And if you look through, right, so this is natural olivines. Titanium, if you look at the concentration of titanium, go through some, thermodynamics and so on, calculate defect concentrations, the order of magnitude of the extrinsic defects, such as titanium, calcium, and so on, is very similar to the defect concentration of intrinsic, calculated concentration of intrinsic defects. Meaning that, yeah, these extrinsic defects are probably very important for all properties of olivine. So if we can confirm that with deformation experiments. So we hydrate olivine, we dope it with titanium to see whether that defect structure indeed does something. And you can start to think, so what was the slowest diffusing species in olivine, right? that's silicon here. So if we increase silicon vacancies with this defect mechanism, you know, it's in that sense consistent that then you would expect this to affect the rheology of the olivine. Right? And that's indeed what we observe. So infrared spectra, again, we see those two bands for these samples. And we get this linear relationship. Remember, the linear relationship isn't new, but now we can vary the water content, and the water content is from the infrared spectroscopy in these two bands. So we directly look at, you know, from the infrared spectroscopy, linking it with how much hydrogen there is, how much hydroxyl there is, with the rheology of for the olivine. So it's from these observations, we then say that that's the defect that controls the rheology of olivine, hydrogen associated with this titanium clinocumide-like point defect. So it's not intrinsic, at least for hydrous olivine, it's not intrinsic defects, but rather extrinsic defects that control the rheology. But as I said, that's still a debate, that's still more research that needs to be done in that area. So a little bit I wanted to relate then seismic properties to what we just talked about here in defects. Another reminder from the talk this morning, you know, so the deformation here, post-seismic rebound was of the order, was somewhere here between post-glacial rebound and Chandler wobble and so on. So we really have deformation in the Earth across a very broad range in timescales. That's very important to realize, from seismic 1 second to whole mantle convection. And that was realized early on. And given that I spent so much time talking about defects, right, I mostly talked about this part here, the constitutive equations for large strain deformation. But certainly there has to be a link. We're interrogating, one difference is that when we do large strain deformation experiments, we're changing the microstructure. We're rearranging crystals, or in dislocation creep, introduce dislocations, recrystallize grains. Seismically, as it turns out, the strains are very, very small, right? The passing wave will have a very small strain. So you just tickle the microstructure. You just excite it, but you don't really change it. So you interrogate it. And we can make use of that to try to see you know, what are the important parameters for seismic properties. And this is done in torsion, right? Seismic waves in the upper mantle would have kilometer wavelengths. Of course, we can't do that in the lab at high pressure and temperature. So instead of having a standing wave, we deform the sample. Instead of just compressing it like you did with a dead weight, you'd be torquing it, right? You'd be twisting it back and forth, and you do that periodically, and you simulate passing seismic waves. So we can do that at high temperatures. The confining pressure, 200 megapascal, is very low. That's really there to keep the interfaces tight. So we have a good coupling when we excite the sample. So attenuation, I think Jeff already went over that, so I don't need to spend that much time. Attenuation, energy loss per cycle. These are micro creep experiments. So instead of, you know, torquing it back and forth periodically, we do that, we just twist in one direction and then watch what happens. And the main part here is to see the temperature dependence, right? This is going back. Temperature for seismic property is a key variable, right? You need to know the temperature dependence of seismic waves, because you can clearly see there's a big difference in the resulting strain, right? This is really a glorified strain, torsional mode distortion, how much strain you get in torsion between 1,000 degrees and 1,200 degrees. For a step function application in stress. And a bunch of models, I think Phil already touched on those. So Maxwell body, going back to springs and dashpots, it's nice and simple, right? You compress the dashpot and you interact with the spring, right? That's viscous deformation, that's the elastic deformation. For seismic, for convection, you know, you have earthquakes, that will be your elastic part. You have convection, that's your viscous part. For seismic properties, it turns out you have to account for what is anelastic behavior, where instead of a serial connection here, you have a parallel connection of spring and dashpot. And we think that through springs and dashpots are nice in that sense, right? If you try to push a spoon into honey very quickly, you can't do that. You have to push it in slowly, and the more slowly you can push it in, the higher the viscosity of the honey, right? So when you combine then a spring and dashpot, A spring you can deform instantaneously, right? But by this parallel concentration, you can't instantaneously deform this element. There will always be a time delay because you have this viscosity of the dashpot. On the other hand, if you just had the dashpot like in the Maxwell model, you can, of course, have an infinite dashpot and can do infinite deformation, right? There's no restoring force. The spring, from Hooke's law, we know that there's a proportionality between how much deformation you get and what the applied stress is. For a very small stress for a dashpot, you can just keep going. Here, for one, it's not instantaneous, but two, you have a finite strain, right? At some point, the spring will balance the applied force. So I'm not going through in detail, right? You can draw these diagrams, stress versus then time, and strain versus time, and you can see that, right, the strain, instead of being instantaneous, is time delayed, but it has a definite maximum. So that's the key definition of anelasticity, is that you have a time delayed response to an applied stress that goes to a maximum elongation, a maximum in strain, right? And then if you, of course, remove the force, you'll have the same time delay, but because the spring pushes back, you get all of your energy, all of your deformation back if you wait long enough, right? Then it just becomes a question of how long do you have to wait. So this is basically what you see here, right? So you can decompose these curves into an initial instantaneous elastic part, right? That's your elastic, that's your spring constant here. Then you can see that the strain rate changes, right? That's your anelastic part where your strain rate changes. And then at some point, you're sitting out here and you just continuously viscously deforming it, right? And that's your dashpot. So if you then let go, right, after 2,000 seconds, you step your stress back to zero, you get that anelastic portion back. Well, first you get the elastic portion back, right? That's instantaneous. Then you get your anelastic portion back. And if you wait long enough, you get all of that back. But the strain that's left here, then that's your viscous portion, right? You have a permanent strain that is applied to this particular sample, and you can characterize this behavior, the instantaneous elastic part, the transient anelastic part, and the permanent viscous part with what's called a Berger's model, right? Where instead of the Maxwell part, you just have spring and dashpot. With the Berger's model, you have this anelastic component in there. And the reason that I emphasize this is so much is that seismically, right, so convection, you have the dashpot. I mean, this, okay, is a representation of your earthquakes, but seismically, this is the regime that you're in. You're in this anelastic regime. And as it turns out, post-seismic, you might also have a contribution from this anelastic deformation, right? You might also be, because here is the temperature dependence, right? That's the viscosity. We just talked about the viscosity is temperature dependent. So the viscosity of this dashpot is temperature dependent. So the time scale with which you can deform this anelastic part depends on temperature, the viscosity of this, right? So as you go in a lithosphere into the asthenosphere, you have a very large temperature change. You go from elastic behavior to a component of this anelastic behavior to eventually viscous behavior. But because of the temperature dependence, it's a transition in time scales. So you can compose then a creep curve that looks like this. You have an anelastic component, you have this, you have an elastic component, anelastic component, and then the steady state component. And recoverable, irrecoverable is that the elastic and the anelastic part, because there's springs involved, you can get that back. Whereas the deformation of this dashpot is permanent strain, you won't get that back. And that can be, you know, here, this is relatively short time, that goes on by mantle convection. So.
We have about 5 minutes.
Okay, right, yeah. So here, time scales, earthquakes, seismic waves, post-glacial rebound, mantle convection, the same as I had earlier. So attenuation, yeah, as I said, I think Jeff already covered that a little bit. What we measure then sinusoidally is that if we look at the shear modulus as a function of oscillation period, is that the shear modulus at a fixed temperature decreases with increasing oscillation period. So going back to this Berger's model is that you get increasing contributions from anelastic and viscous behavior, right? So more and more of the strain is taken up by the dashpot rather than by the spring. At the coldest temperatures, most of it is just spring, it's elastic behavior. As temperature increases, it becomes anelastic behavior because that anelastic element becomes more and more important. And that also is consistent with the fact that there is the dependence on frequency. So the longer your frequency, the further you can push the spoon into the honey, so the more lossy the material becomes, the lower the shear modulus. And this just illustrates that you have a grain size dependence, very fine-grained. The modulus is much lower. More coarse-grained, you have a higher modulus. These are experimental grain sizes of the order of microns. You then have to extrapolate that to millimeter to centimeter grain sizes in the mantle. And yeah, I won't go much. So again, we're trying to link these experimental observations, that's always the goal, with some constitutive model that allows us then to extrapolate to upper mantle conditions, right? In pressure, temperature, grain size, and so on. And this, I won't have time to go into those details. There are various, again, this is where the interesting thing is, right? So this is what our data looks like. And then we're trying to link it to models, and these models, again, going back to the 70s, of grain boundary sliding. So for seismic properties, grain boundaries are very important, in particular also, diffusion, because as you apply a shear stress across this polycrystalline aggregate of your nice hexagonal grains, you have non-hydrostatic stress concentrations at grain corners, and that, as you saw earlier, right, stress concentrations then drive diffusion. And that's the idea that behind seismic attenuation, is that you have seismic waves applying a shear stress, leading to stress concentration at grain corners. That starts to drive diffusion. The big difference to diffusion creep is that diffusion, so you still have these elastic restoring forces at the grain corners, right? So that's the anelastic part. For the viscous deformation, you permanently change the grain arrangement. Seismically, because you're just at very small stresses, very small strains, you just slide the grain boundaries past each other by a little bit without changing any of the geometry. You're just starting the process of diffusion, but you never complete it, right? You never complete diffusion entirely. And if you then put it together as a function of period, right, you get this diffusion then, because you have different scales, the longer you apply your stress, so period increases to the right, so that's log period, so time scale increases to the right. The longer you apply the stress, the further you can diffuse, so that eventually, right, you transition into viscous behavior. You have normal diffusion creep. But in this intermediate time scale in the anelastic behavior, you have this dissipation, the energy loss or attenuation, increasing with increasing time scale. That's what's called an absorption band, so that you should see a frequency-dependent behavior, and the seismologists are still working on that. I mean, there are certainly experiments going in that direction, looking at the frequency dependence of this attenuation, which would be, or which is, what the data that's out there is a confirmation, essentially what we see experimentally, in that, this exponent here of this frequency dependence is similar, observed seismically, to experimentally. The exponent is about 1/3. That's when you do seismic experiments, which are very difficult because you have to measure the same wave at different frequencies. It's roughly the same exponent. And the underlying model, and that's the important part, right? So again, we macroscopically investigate the crystal. You saw the data, which looks something like that. And then we have a model that explains the data, in this case, grain boundary sliding, accommodated by diffusion. So wrapping up, this is work in progress. One of the exciting periods, that's a PhD student, Chris Klein at ANU. Now the next part is, of course, I talked about the titanium, how that affects the large strain rheology, in particular in dislocation creep. So we thought this was great because we can just measure the effect of water on seismic properties, that water enhances this diffusion as well. But it turns out that things are more complicated and unexpected and took us a long time, but basically you can see here, instead of for the rheology, we had a nice linear relationship between, as we increase the water content, the strain rate increases. This is not what we observe here seismically. Essentially, we have a null result, right? We increase the water content, but the dissipation, the energy loss, stays exactly constant. So to first order, water has no effect on seismic properties. And there's a lot more, of course, behind this, because that's somewhat contrary to the expectation. The expectation was that just as for large strain rheology, water has the same effect on seismic properties, but that's not what we observe. So, but this is still work in progress, and we have to, rethink our thinking on a lot of the defect processes. What we do in large strain deformation experiments is we migrate dislocations, and so somehow for dislocation motion, the water content is important, but then for this grain boundary sliding process, it seems like water content, presumably then in the grain boundaries, is not important. So that's, the summary essentially, and I take questions.
So in keeping with the previous talks, we'll start out with questions from students and postdocs.
Thank you, Ulrich. Very interesting talk. You mentioned how important the grain boundaries are. They could have different melt fractions and different surface energy, could affect grain boundary, grain size. I wonder how much we know on the hydrogen in the grain boundaries and not in olivine themselves.
I mean, there's no direct way, right? So when we do Fourier transform infrared spectroscopy on polycrystals, we certainly also shine the light through the grain boundaries. But the grain boundaries, you saw the images, right? If you then calculate, as if the absorbance correlates to path lengths in the crystal, if you then calculate, in a polycrystal material what the path lengths is of grain boundaries, you just never see that, because the path lengths through a nanometer grain boundary, even at a 10 micron crystal, is negligible, right? So you can't, there's no direct way that I know of with which you could determine hydrogen content, hydroxyl content in a grain boundary, right? So you really have to rely on very indirect measures, such as the seismic property experiments. The material scientists refer to these torsional experiments as grain boundary spectroscopy, because you're measuring, keeping in mind it's a model, you're measuring grain boundary sliding, right? So that's really the only way, and it seems like water is hydrogen is a trace element. So the trace elements, calcium, aluminum, and so on, there, as I said, there's a partitioning, equilibrium partitioning between grain interior and grain boundary. So we just assume that hydrogen in that sense behaves like all the other trace elements. The more you have in the grain interior, the more you have in the grain boundaries. That's as good as it gets, but then apparently in the grain boundaries, it's not an important, it does not control the properties of the grain boundaries in the same way it does control the properties of dislocation motion, right? It's one trace element among many in the grain boundaries. Does that?
Yeah, and another question, if I can. What do you think about the distribution of dislocation density to the attenuation?
There are experiments, another student at ANU did experiments trying to look at the effect of dislocations on seismic attenuation. And those experiments, we published them, they're still very difficult to interpret. There are, every time you do different experiments in that sense, there are new complications that arise. So there is dislocations increase, so increasing dislocation density increases the attenuation or dissipation. But then, so from these experiments, I mean, the perhaps simplest answer is that at dislocation densities expected in the upper mantle, you would have a very small or no contribution. So, I mean, no contribution, of course not, but a very small contribution. But it's complicated because even in undeformed samples in the lab, we still have dislocations present. So there are dislocations just incorporated in the crystal structure during grain growth. So we may have been measuring, even though we didn't deform the reference samples, there were some dislocations present. So that's still, there's still some open questions. The straight answer is yes, dislocation make a difference, but then the question is, at the dislocation densities in the mantle, does it make a difference? As some of the others, like temperature or other parameters do.
Back there.
I'm someone who look at alvine basalt. It's very interesting to listen to your perspective. So I have some maybe entry level questions. First of all, I was wondering if you have have hydrogen, you have to incorporate them. So you basically replace the silica with titanium. Where did the titanium come from? Is it a closed system overall? So just going from a low strain area to a high strain area?
Yeah, the idea is that if in anhydrous olivine, the titanium as a 4+ ion sits on the silicon side. Right? And then as you hydrate the olivine, the titanium moves from the silicon side onto perhaps a pre-existing magnesium vacancy. Right? And then to charge balance it, you have those two hydrogens. So the titanium's in the olivine. So if you take natural olivines, they have a range of titanium contents from a few tens of ppm to a few hundreds of ppm. And on hydration, you just move the titanium around in the crystal structure to accommodate the hydrogen.
Okay.
That's the model. That's what we see. And there, I should say, there's a bit more behind that. People have done a lot of synchrotron work to try to characterize the site where the titanium is, both in anhydrous and hydrous olivine. So there's a lot more behind that. And it's all a little bit indirect because you, of course, never image that titanium atom in the crystal structure, but it's all consistent that XS and XANES data with the infrared data, with the ab initio modeling, that this is the change that you see. You take that titanium and move it around. That requires, of course, diffusion, and there's a time scale, so you don't do that instantaneously. So there are implications for how you do water incorporation experiments in olivine, for example.
I have another question. I noticed that for a lot of experiments, people were just looking at pure forsterite.
Yep.
And a lot of these are olivine focused, but we know in mantle they're pyroxenes, and they're mostly, forsterite 90, which means there's 10% iron olivine. How do you think those compositional varieties would affect like water incorporation into the mantle, strain rate change, diffusion rate, all that? Do we know well about those properties? So
that's again something that's active research, right? So as you say, a lot of people do experiments on forsterite because it's much simpler, because you don't have to control oxygen fugacity. With FO90, if you have iron-bearing olivine, you need to control the oxygen fugacity because iron can change oxidation state, as does chromium as well. You can go from iron 2+ to iron 3+, depending on what your partial pressure of oxygen is. And it from our experiments at least, they very strongly suggest that you cannot use properties from forsterite and straightforward extrapolate them. So these seismic property experiments, we've done them with forsterite as well, and the behavior of pure forsterite is different than iron-bearing olivine. There is a sensitivity to oxygen fugacity, but for example, wet forsterite, there's even so under the same conditions at high oxygen fugacity, wet forsterite behaves like dry FO90 olivine. So there is no forsterite. You can have high oxygen fugacity, high water content, and it doesn't make a difference on the physical properties. And there are similar things. There's papers that look at diffusion in pure forsterite that also find essentially that pure forsterite water has no effect. But it's more complicated than that because iron-bearing olivine, as you vary the oxygen fugacity, you change the concentration of Fe3+, and that has a large effect. So Fe3+ is very important, it seems like, and with it, oxygen fugacity. And then, so that's where we are experimentally. At this point, there are a few, we have some indications that pyroxenes don't make a large difference. But, you know, so these are just indications. We just haven't covered that experimentally. From the exploratory experiments we've done, is that the result is that the bulk chemistry, so the trace element complement in olivine, and whether you have melt or water present, is more important than varying enstatite content, for example. But that's certainly something that we need to look at more closely as well.
Thank you.
So my question is, how would you estimate the grain size and the dislocation density, something like this, in the real mantle?
Yeah, that's a very good question, and I mean, it's indirect, right? So the direct observations you have are from xenoliths and from peridotite massifs, and maybe Jessica will talk about that a little bit. So you can measure those, you know, olivine rocks that have been brought up to the surface, measure the grain sizes. The problem is that the transport process, or, you know, processes that lead to emplacement, may have modified your grain size from what it is in the convecting upper mantle in the asthenosphere. So then you have to resort to indirect observations. For example, we've measured grain size dependence of seismic properties. So then, you know, you vary, as one of the parameters, you vary temperature, you can vary melt content and so on. You can also vary grain size and see, you know, which parameter range fits your observations, your seismic observations. And, you know, what we get is millimeter to centimeter, so it's consistent with, you know, the estimates that you get. Or you can do convection models and see, you know, we have seismic anisotropy in the upper mantle. Seismic anisotropy, you need a component at least of dislocation creep, right? So it can't all be diffusion creep. You have to have dislocation creep in order to get seismic anisotropy. So the grain size has to be large enough. If the mantle was very fine grained, you'd never transition into dislocation creep, right? So it's, at this point, arm waving. Grain size is a very important parameter for all of these because it's so linked to diffusive processes, but the estimates are millimeter to centimeter.
I think we have time for one more question.
Just a quick clarification question. You mentioned that when changing the E from the activation energy, one should also adjust the A, because obviously that's what was used for fitting. But presumably only mean if I take the absolute values seriously, rather than saying that there's a covariance between E and A. Or is that what you meant?
There's a covariance. That's
a strong covariance?
Yeah, of course. I mean, in the fit parameters, right?
Right. So okay. So how can you isolate then the temperature dependence, right? Then you should sort of, I guess you need to adjust for that after the fact, like what Kornaga did, for example.
I mean, you can explore the sensitivity, right, of your different, because you fit temperature dependence, you fit the stress exponent, you know, that prefactor A, you fit that all at the same time. So you can explore that, you know, if you have enough data, then you can explore the codependence and see what your best values for each of these parameters is. But you can, I mean, so if, you know, I have a flow law with a particular set of parameters for activation energy and for A, and I can't just change one without the other. It would mean, basically, if I just change the activation energy and leave A alone, I can't fit my experimental data anymore.
Sure, but presumably you have some data points that narrow down the slope, which you use to get the E, for example.
Yeah.
Right. And so that information is still in there, even though you lose then the information about the absolute creep rates.
Right. Yep. Yep. Yep.
Okay, well, let's thank Uli again for a good talk.